So 1.5 is called polynomial functions and complex zeros. What's complex? What's a complex zero? What's complex? Do we remember that word? No. Imaginary. Yes, eyes. Eyes are coming. All right, so zeros and factors we start with. Okay, if f of a equals 0, then we know this, then a is called a zero or a solution or a root of the function. We've now talked about this like 700 times, okay? The multiplicity of a zero is the number of times a root occurs. So if I have the same answer occur multiple times, then I count how many times it occurs, and that's called the multiplicity. So if I have x equals 2 and x equals 2, obviously that's a multiplicity of 2. If a root or zero has an even multiplicity, so that root occurs 2 times or 4 times or 6 times, then it hits the x-axis at that point and turns around. By the looks of it, it looks like it's bouncing off the axis at that point. If the root has an odd multiplicity, so it occurs 1 time or 3 times or 5 times, then the graph crosses through the axis at that point. We remember this? Yes? So this is why graphs take the turns they take. Okay, if something occurred an even amount of times, if my even multiplicity on 0 was, or if the multiplicity on 2, let's say, was even, so this occurred twice, and this occurred once, my graph would cross through, whether it's up or down, we'll get to eventually, but cross through, come back, and bounce off this point and continue in that direction, okay? Or it could bounce off underneath. That's part of what we're going to determine today. So this is what it looks like if it bounces. That would have an even multiplicity. And this is what it looks like if it crosses through. That would have an odd multiplicity.
Can it have both?
No. All right, so example 1 says find the zeros of the polynomial function, then determine the intervals for which f of x is greater than or equal to 0. So go back to the 0 part of this. This one's already factored for us, right? How do I find those zeros?
Set each parentheses equal to 0.
Good. Set each parentheses equal to 0. So if this equals 0 and this equals 0 and this equals 0, then I end up with x equals positive 1, x equals negative 2, and x equals 4. Now, why is this squared important? It has a multiplicity of 2. If it has an even multiplicity, what's happening at negative 2? It's bouncing. So this one has to bounce. Now we got to think about what this could look like. To be honest, I think this is so much easier when we get back and go over end behavior, which is in 1.6, but we're going to follow the pattern like they're doing it. I'm going to say this is 1, this is negative 2, and here's 4. Tomorrow we're going to learn about the ends, right? The end behavior, does the arrows go up or down, okay? But that is part of it. So I know it has to cross through 1, it has to cross through 4, and it has to bounce off of 2. So here are some options. It could either start up, come down, bounce off 2, but then it has to come back through, cross through 1, and then it has to come back through, cross through 4. That's one possible way this graph could look. The other way is it can start down, so it could point down on the left. It would have to bounce off of 2, come down, it has to come back up and cross through 1, it has to come back down and cross through 4. So it could look something like that. So if it says, where is f of x greater than or equal to 0, how could I figure out which of these is right? So if you didn't know, because I don't know why, but they pretend like you don't know end behavior first. Let's say that we don't know the arrow-wise. How could I know if this graph was right, where it would be positive all up here, or if this graph is right, where it would be positive there?
Leading code.
That's your end behavior. So pretend you don't know that yet.
Plug in a number.
Literally plug in a number. Okay? So if you look at your pattern, it's happening in every other space, right? So I literally can plug in a number. If I plug in something behind -2, so like -3, and the number is on top of the y-axis or positive, then I know the first graph is right. If I plug in -3 and it's below the x-axis, then I know that the right graph is right, okay? But instead of plugging in -3, let's plug in something easy like 0. 0 is one that would help me with this, okay? As long as 0 is not a 0, then I would say always plug in 0. So if I plug in 0, my goal is to see is the result positive or negative. If it's positive, I know it's the one on the left. If it's negative, it's the one on the right. So if I plug in 0, I get 0 minus 1 times 0 plus 2 squared times 0 minus 4. And I get -1, 2 squared, -4. I don't even care what the actual amount is. All I want to know is this positive or negative? It's positive because there's 2 negatives there, which means this graph is the correct one.
For graphs, if we found it was like 16, would we have to like draw it going all the way up?
No, you just want to approximate it.
Okay.
Yeah. So I know that that's the pattern it takes. It falls left, rises right, which is the end behavior. So if you do remember end behavior, great. You could use it here. The end behavior rule is if it's an even exponent, they're both up or both down, positive both up, negative both down. And if it's an odd exponent, it falls left, rises right. If it's positive, and if it's odd and it's negative, it falls right, rises left. No, rises left, falls right, okay? So if you had looked at this knowing that this is raised to the first, this is raised to the second, this is raised to the first, the degree here would be 4, and the leading coefficient would be positive, which means both of them point up. So if you remember that, you want to use it, fantastic. If not, we're going to review it again tomorrow because that's what 1/6 is.
How is the degree 4?
Because this would be x to the first, this would be x to the second if I FOILed it out, and this would be x to the first. So x to the first times x to the second times x to the first, I'd add up all those exponents, and I'd get x to the fourth. So how do I explain the range in which f of x is greater than or equal to 0 here? How would I describe this part of my graph, this part of my graph, and this part of my graph? No, sorry, give me like an interval is what I mean. Negative infinity to 1. Does it get a bracket or a parentheses? Parentheses on the negative infinity, bracket on the 1. Why does it get a bracket? Because it says or equal to. Where else is it greater than or equal to 0? Bracket 4. Positive infinity. Good. You could put a union.
And we could just switch f of x to y, right?
Yep.
Okay.
All right, let's do it again. This time, what's different from A to B? It's not factored yet. Okay, so we're going to start by factoring it. What are the factors of -3 that sum to -2? -3, +1, split and solve. X equals 3 and x equals -1. So my zeros, do either of them have a multiplicity other than 1? No, so they're going to cross through each of these. Okay, so think about the exponent here is squared, right? What kind of shape is this? Parabola. Where are my arrows pointing? Up, both up. So this graph is going to cross through at -1 and cross through at +3 and look something like this. So I don't even have to plug in a point this time. I could. If you were unsure what that graph looks like, I could plug in 0, and what would I expect to happen when I plug in 0? Should be negative, and it would be -3, which confirms it. So how do I describe the part of this graph that is greater than or equal to 0? Negative infinity to -1, bracket, and good.
I got a question.
Yep.
So multiplicity is the exponent on the leading constant, right?
No.
No.
Multiplicity is the number of times a 0 occurs. The degree is the exponent on the leading. Is that what you're saying? Yeah.
So in this case, what was it?
That has a degree of 2.
2, because it happens twice.
No, the degree comes from the original equation. How many roots there are? There's 2. The multiplicity comes after you solve it. How many times each of these answers occur?
And in this case, the multiplicity is 2.
No, the multiplicity is 1 for each of those. Each 0 has its own multiplicity.
Okay.
The degree is 2. The multiplicity is individualized to the root. So 3 has a multiplicity of 1 because it only occurs once. -1 has a multiplicity of 1 because it only recurs once.
And then if, like,
The multiplicity determines the bouncing and the crosses through. The degree determines the end behavior. Where do your arrows go at the end?
okay.
Yeah. Danielle.
You know that it's not like an N shape because the x squared is not negative x squared?
Correct. Yep.
When would the arrow go down?
If it was a negative x squared.
Oh, okay.
Yep. And if you didn't know, you would plug in a point. If I plug in 0 and it's below, I know that it's supposed to be the way it is. If I plugged in 0 and it was positive, I would flip this upside down. But again, I think that's easier after tomorrow. Like today, they assume you're going to plug in some points. Okay? But if you remember end behavior, use it. And if not, tomorrow I'm going to go over end behavior, and that helps. All right, imaginary roots. Okay, complex zeros are both real and non-real numbers. So complex brings in, a complex number could just be a real number, but a complex can also include non-real numbers or imaginary numbers. These are your i's, okay? Only real numbers will appear on the graph. So if I end up with answers to an equation that say x equals 2, 3, and then 4i and -4i, I'm only going to see 2 and 3 on my graph. I will not see 4i and -4i because they're imaginary and your graph is real. For an nth degree polynomial, the function has n number of real and unreal roots. So if my polynomial is x to the 6th, there are 6 total roots. And those roots can be broken down into real and non-real. That does not mean there are 6 real roots. Yeah.
So when we're finding the zeros, we would count both real and non-real?
Yep.
Okay.
And lastly, non-real roots come in pairs. If 2 plus 3i is a root, then 2 minus 3i is also a root. Notice the sign changes on the one with the I, not the real part. So the sign changes on the complex part, not the real part, or the imaginary part, not the real part. All right, so looking at this, it says determine the roots from the graph. So notice on the left-hand side, these 3 say that it is a quadratic function, which means there are 2 roots, or the degree is 2. So look at this graph. How many roots are there? How many real roots? Sorry. 2 real roots, which means there would be how many non-real? 0. Go to the next one. How many roots are there? Ooh, what's wrong with that answer? Yeah.
There's one real root and then one non-real root, so there's 2 total.
Look at my graph. What's happening on that graph? It does touch. What does it specifically do? It bounces. What does it mean if it bounces?
There's 2.
There's a multiplicity of 2. So there are 2 real roots. How many non-real? 0. Does that make sense? So it bounces. If it bounces, it means it has an even multiplicity. It means that an answer is duplicated. So on this graph, that looks like it's 1. That means 1 occurred twice. If it bounces, it occurs an even amount of times. Yep.
So it would be like x minus 1 squared?
Correct.
Okay.
Yep. That graph, that equation would be exactly that. X minus 1 squared, right? It's a parabola shifted to the right 1 place. And there would be 2 1s. That means there's 2 real roots and 0 unreal roots. Does that make sense? Yes? Okay, go to the next one. How many real roots are there? 0, which means how many non-real roots would have to be there? 2.
Can you explain why?
Because it doesn't cross through the x-axis, so there's no real roots. But my degree is still 2, so the other 2 have to be imaginary.
Why does the f of x keep the x minus squared? Why is that?
Because there are how many, so this is really this, right? X minus 1 squared is really x minus 1 times x minus 1. If I solve that, I get x equals 1 and x equals 1. That is 1 root, but it has a multiplicity of 2. So it is 2 roots. Does that make sense? Okay. Daniela.
If the power is 3, for example.
Yep.
And then you have the number of unreal and real have to add up to 3.
Yeah. That's the whole right side now. Yep. So now the cubic is the right side.
The number of non-real zeros is always even, right?
Correct. Yep. Yep. Sure. I don't know if you guys heard Camilla, but that was a good question. The number of non-real roots is always going to be even because they have to come in pairs. Okay. All right. So if my cubic, now it's cubic, so the degree is 3. That means these all have to add up to 3, right? So if I look at that first one, how many real roots are there? 3 real roots, which means there are how many non-real? 0. Go to the next one. How many real roots are there? 1, which means there are how many?
2.
Good. And the last one, how many? 3. Why? Good job, people. 1, and it bounces here. So there are 3, which means how many non-real? 0. Quick learners. Good job. Questions? All right. I didn't number that one, so technically this is example 2. For each polynomial, the degree is listed along with all of its real roots. Find the number of non-real zeros in the polynomial. If you can subtract 2 numbers, you should be able to do these, right? So if the degree is 4 and there are real zeros at -2 and 1, how many real zeros are there? 2, which means how many non-real would be left?
2.
Good. Not B, that's A still. B, man, just one time I want to get through that typo. It says the degree is 5 with real zeros, x equals -2, and x equals 1 with a multiplicity of 2, which means what? There are 3 real zeros there, -2, 1, and 1 again, which means there are how many imaginary or non-real? 2. Still good. Yes? All right, example 3. Given one non-real zero of the polynomial, find the other one. So if -3 plus 2i is a non-real zero, what else has to be a non-real zero?
-3 minus 2i.
So smart. Good job. -3 minus 2i. And if 4 minus 5i, then?
4 plus 5i.
Good job. Notice we didn't change the sign on the real part, right? That always stays. It's the one with the I that changes. So the question came up, what if I got 5i as the real root? Come on. Then my other non-real root would be -5i.
And if you just had I, it'd be I negative.
I and -i. Yep. All right, now we're going to use the table to determine the degree of the polynomial. Yep. All right, so it said, first of all, we talked about this yesterday, right? We did this with linear, we did this with quadratic. If I have a table of values, I can figure out if that value or that data represents a linear function, a quadratic function, a cubic function. Eventually, we will keep going. But the way I can determine the degree is finding the difference or the rate of change on each level. If the rate of change the first time is the same, it is linear. If the rate of change the second time is the same, it's quadratic. If it takes to the third time, it's cubic. If it takes to the fourth, then it's the degree is 4. Okay, so you could keep going. And then eventually we're going to get to other tests. But for right now, this is just to determine degree. Okay, so tedious, yes. Impossible, no.
What does N represent?
The degree. All right, so example 4 says find the degree of the polynomial from the given input and output values. This is my original input and output, so this is not already like a rate of change. We have to find the rate of change. First thing we're going to do is pay attention to your intervals at the top. Are they the same? Yes. Okay, if they're not the same, we have to figure out the rate of change by doing y2 minus y1 over x2 minus x1. But because these are all going up by ones, I literally just have to find the difference between each one of these. So 13 minus 13 is 0. 11 minus 13 is negative 2. 7 minus 11, negative 4. 1 minus 7, negative 6. Are those the same? No. If they were the same, it'd be linear. Now I go to the next level. Negative 2 minus 0, negative 2. Negative 4 minus a negative 2, negative 2. Negative 6 minus a negative 4. I missed one. Negative 2. Now are these the same? Which means the degree here is 2, and this is a quadratic function. If I had to do it again, it'd be 3. If I had to do it again, it'd be 4. Yep.
If you get to one where they're all the same, you can stop and say it's linear, quadratic, and cubic.
Yeah?
You don't have to like keep on going.
No.
Okay.
Hello. All right, last thing, and we've done it before. Even and odd. Okay? So even means it's symmetric to the y-axis, and odd means it's symmetric to the origin. So remember, if there's two ways to test this out, one is literally looking at a graph. If I can fold it left to right and like a hot dog and it overlaps, that's symmetric to the y-axis. That would be even. The other is the top right quadrant reflects down to the bottom left. So 1 goes to 3 or 2 goes to 4. Okay? Those coordinate points, you literally just change your signs on. So if I have coordinate points like 1, 2 on my original function, then it would be reflected. So this is 1, 2. It would be reflected to negative 1, negative 2. So negative 1, negative 2. If you have points like that, then they're symmetric to the origin. Okay? If your x and y values both change signs. Now, algebraically, we do this. Algebraically, we take the x and replace it with negative x. And if it goes back to the original, then it's even, because it'd be symmetric to the y-axis. And then for odd, all you have to do is change the x to negative x, and all the signs should be change the signs, and they should all be the opposite. So you can change both the x and the y, but you can even shortcut this by just changing the x and making sure they're all the opposite. Okay, that would be the same. So it will literally ask you from the graph and from the equation. Think about what makes something even. What would make a negative go away? Neither is neither.
No, what is either?
It's that's even. I'm like, what do you mean what's neither? It's even, odd, or neither. What would make negative x go away? Absolute value or even power, right? So you can start to just spot these, hopefully. If I plug in a negative x here, it's going to go away, which would make this what? Even. On B, if I plug in a negative x, what happens? They both change signs, which makes this odd. If only one term changes, not the other, it's neither.
Does origin pop up in this?
Odd is origin.
Okay.
O for O. So now look at C. Does that have y-axis or origin symmetry? Origin, which makes this odd. And D, neither. Neither, neither, call it what you want. Okay? Daniela.
Origin symmetry means you can reflect it over both.
Like if you're visualizing it, you literally would fold it down and over and overlaps. But you could also just pick your points and see that the positive, so this is like a 1.51 and this is a negative 1.5, negative 1. If both those points have opposite signs, then it's symmetric. I point it, I follow it, no. You could go left, right, and then down, doesn't matter. Yeah, yeah. Questions? Easy stuff, right? This is a good week. All right, complete the graph if the function is either even or odd. So if I give you half a graph and you're making it even, what are you going to do? Mirror it over the y. So this point I'm going to plot here, this point I'm going to plot here, and then I'm going to literally draw the curve like that. And if it's odd, how do I reflect the points? Across the origin or change the signs on your points, okay? So if it's negative 1, 1, I want to plot 1, 1. And if it's negative 1.410, I want to plot positive 1.4140. So it kind of does this. If I wanted to plot another point over here, that would be like negative, I don't even know what this is, 0.5-ish. Negative 1.5 and 2, then I would be going positive 1.5 and negative 2. So you can mirror any point. Good? Questions? All right, open to the classroom. Questions from last night. Which one? All right, number 1 said for the polynomial function g, the rate of change g is increasing for x is less than 2 and decreasing for x is greater than 2. Which of the following must be true? So I kind of like just drew it. Like it was increasing up until 2 and then it decreased after 2. So it says that it has to have a max. It says it has the inflection point of x equals 2. It's concave up from this part where it's less than 2 and where it's other way around. Yes. Okay, I drew it reverse, but it is the inflection point because the rate of change, this is not the original, this is not the actual graph, that's the rate of change graph. That's the difference. So if it didn't say rate of change, now you're looking at minimum and maximum, but it's talking about the rate of change. If the rate of change is increasing, now it's concave up on that spot. And if it's decreasing, it's concave down on that section. That's why it's D. So again, look for words like rate of change. It's not the actual graph. Number 2, the polynomial function is given by that expression. Which of the following descriptions of f of x is true? So without completely foiling it out, because that's the hope, that you don't actually have to go through all of this. If I had squared this, right, my leading coefficient would have been 9x squared. And then I would have multiplied that times the leading coefficient here, which would be x. And I'd get a positive 9x to the third. So the goal is to not have to do all the work. And from there, you should see it's a degree of 3 with a leading coefficient of 9. But again, you want to do that without having to FOIL all of it out. Number 3, the values of the polynomial function are selected values in the table. If all the zeros of the function are given at the table, what of the following must be true? Okay. If I plotted these, like if you did -1 and -36 and 1, 0, 3, 4, 5, 0, 7, 12, it looks something kind of like this. Okay. It cannot cross through at this point, or it would have another 0. So that's why we rule that out. Okay, and you would say that it has the local minimum at 5, 0. If you looked at all those points, like it said, the local minimum is at -1, -36. This could have kept going down. We don't know that. The second one said it has a local minimum of 5, which makes sense because it can't cross through here. It had to have bounced there and gone back up. That's a local minimum. At 3, 4, sorry, this is going to keep going back up. This could have come up higher, come back down. We don't know if that's the highest part in between there. And then the last one, 1, 0, that again is not necessarily, that definitely is not a local minimum because it would have to do, or maximum, it would have to come back down like that. So for me, I had to draw it out to visualize it. 4, this said the graph of the polynomial function is shown. The function f is defined from 0 to 3, including 0 and 3. And it's identical to the function g on the interval. How many local minima and maxima does the function have? So literally you're looking just from 0 to 3. And there was 1 local max and there was 1 local min. Wait, sorry, 0 to 3. I drew it in the wrong spot. 0 to 3. So this would have been local min. This would have been local min. This would have been local max. This would have been local max. Yeah.
The definition for min and max, it says when it changes from increasing to decreasing, but at the beginning and the end, it doesn't really change. It starts increasing.
If you go back to that note, there is the exception of restricting your domain. When you restrict it, it can count. Yeah, it's on that slide. That's the catch. All right, 5, the polynomial function is given by blah, 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 where they are constants. Which of the following statements about f is true? It is raised to the 4th power. That's your even exponent, okay? And we know that if that's the case, it's either both going up or both going down. And if that's the case, it either has a max or a min. We don't know the sign on the A, which is why it is max or min. But it cannot be both. Questions overall? We did better on this one, yes? Okay. All right, both homework. All right, JK, this is 6. The graph of the polynomial function is shown. How many points of inflection? Remember to count inflection. We count from concave up to concave down. So this purple, this was my concave down. This is my concave up, concave down again, and concave up. So there are 1, 2, 3 inflection points.